to masterclasses. It's my pleasure to introduce my colleague Radu Ignat from IMT. And he'll speak about vortices in variational models, essentially in the Ginzburg-Landau model. So this is a mixture of partial differential equations, calculus of variations, and topology. A very exciting topic that started developing maybe 35 years ago in the 90s, and I'd say there's a huge research activity actually on that. So, Radu, please.
Yeah, thank you, Mihai. Thank you for the invitation. So, as Mihai said, yeah, the theory of vortices in physical models, mainly variational physical models, it's very rich, and so I chose a particular case, which is the Ginzburg-Landau model. In fact, I will explain only the 2D case, but which contains the main features in this theory. So, what's a vortex? Well, a vortex is a topological point singularity that is very common in many physical models like superconductivity, Bose-Einstein condensates, liquid crystals, micromagnetics, etc. So, and rather the aim would be to characterize such singularities. So, what's the structure? What can you say about the symmetry? Since it's a variational model, this means that there is a functional energy there. So, what's the level of the energy for such singularities? And what is very important is also to understand, so from physical point of view, what are the optimal location of these vortices. And for that, you need to understand what is called the renormalized energy. So this means the interaction between these energies. So this is a bit the flavor I want to transmit to you. So let's see how much can I do. So let's start with the model. So the 2D Ginzburg-Landau. So let us choose omega to be a nice domain in R2, considered to be the disk, okay, if you want. And the maps we consider in physics is called the order parameter. There are these vector fields U defined from omega that are values with in R2, so there are 2D fields, and here I will see R2 as a complex plane. So sometimes I will do multiplication in complex for such fields, so I can do it. Okay? So in the model there will be a small parameter epsilon. So for the point of view of theory, it can be large, can be small. In physics, it's rather small. That is a characteristic length in this model. And it's a variational model. Variational model means that you have functional energy that you will try to understand critical points, minimizers, local minimizer, etc. So this functional is given by, so it's an integral on omega of 1/2 gradient u squared plus 1 over 4 epsilon squared 1 minus u squared dx. Okay, so for the notations, gradient is right. You take the first partial derivative, the second partial derivative of u. It's a 2D field, so that's a matrix, right? 2 by 2 matrix. And here I consider U to be the Euclidean norm, okay? So of course, U, I write it like U1, U2, and also sometimes like U1 plus I U2 as a complex. And okay, consider, so this is the Euclidean norm. Okay, so right, this is called the Dirichlet energy, and this is a potential energy that is very important. So so if we look to this potential, what is the picture, what's the graph of this potential? So if you consider U to be like a real number, then you see what is called the 2L potential, that is something like this, right? So if you consider 1 minus t squared, okay, that has 2 zeros, but U is complex, so you should see now that this is like U1 and that's U2, and in fact this is like, you should consider that you will make a rotation, so you will see like a Mexican hat, okay? So right, this will be the unit circle, which is where this potential cancels, right? Okay, so this is very important in this model. So let me tell you what I will explain here mainly is, so again, we are interested in describing critical points of such functionals. In fact, I will focus on minimizers. Okay, and we will study here a specific regime where this epsilon goes to 0. So what's happening when this epsilon goes to 0? This becomes huge. Okay, this becomes huge. So if you want that this energy is uniformly bounded in epsilon, then better that this thing goes to 0. So this means that in that limit you expect that the modulus of U goes to 1. So in some sense you will go to the zeros of this non-negative potential. Okay, so that's why S1 will play a fundamental role. So so let's write this. So as epsilon goes to 0, the limit configurations are expected to be with values into S1. And if you think to what's happening in the limit with critical points, that will be like critical points of the Dirichlet energy when you stay with values in S1, and this is called the harmonic map problem for S1 valued maps. Okay, so so that's the link with the harmonic map problem. Harmonic map problem. And here, so if you impose some topological constraint on the boundary, for example, so if you impose some boundary data that carries some topological degree, as I will explain in the following, then you expect to have these vortices that will appear. So this kind of point singularities. So you expect to have nucleation of vortices. So yeah, let's draw a picture. So if this is your domain omega, then you expect to have such singular points for these limits U star. And in fact, what you expect is that around these vortices, U star behaves like this kind of functions. Power d. Okay, so these are you should see as complex functions, okay, complex maps that you multiply d times, okay, d kappa times, so where d kappa is some integer. And this is what we call the limit vortex in AK of topological degree dk. Okay? So here AK will play the role of vortex of topological degree dk. So that's in the limit. So of course we are more interested in what's happening when epsilon is strictly positive, maybe small, but not zero. So in fact, what will happen here at the level of epsilon strictly less than 0 is that these singularities, you see that this function is singular in AK. So these singularities will be transformed in a zero of your functions. Okay, so at level epsilon, strictly larger than a vortex will mean in fact a zero that will carry a topological degree that I will explain now. Okay, so what's the problem here? The problem is that such a function, so I told you that harmonic maps are critical points or minimizers, if you want, of this Dirichlet energy, is that such functions have infinite energy. But in some sense, they have the least infinite energy that you can put once you impose some topological constraint. Okay, so here the problem is that the gradient. So let's put here on this small disk. The gradient of this is infinite. Okay, so if you want, let's do a small exercise. So let's take, for example, that the point is 0 right up to translation is the same. So if you take such a function, okay, then right, it's always good to think in terms of in polar coordinates. Okay. Okay, so then when you compute the gradient of u, right, this is, so you see it's only the derivative in theta. So that is exactly d over modulus of x. D can be also negative, so let's put like this. And then when you compute now, okay, let's say that this is u star. So when you compute the u star squared, let's say that this is the unit disk. This will give you d squared over r squared. Okay, so I do polar coordinates, so then it's 2 pi coming out from 0 to 1, and then dx is r dr. Okay, so this is pi d squared, and then you see that this is dr over r, and it's in 0, and that's plus infinity. Okay, so and we say that this kind of plus infinity, it's a logarithmic flavor, right? Because, for example, if you stop, and in fact this is what will happen, you will stop at level epsilon, so then you will see that it's like a logarithmically blowing up energy. Okay, so let's do the theory. So what will be the aim? The aim will be to analyze the asymptotics of such energy. Yes?
It means that in a neighborhood u star looks similar to that function.
Right. Yeah. So to make things easy, you just consider that, yeah, around this point you have exactly this function and you compute the energy. Okay? Okay, so the goal is to study the asymptotics of E epsilon as epsilon goes to 0. So, as I said, the boundary data will play, the boundary data that we impose here will carry some topology, and that's essential for the model. So, I consider a boundary data G from the boundary in the values of the zeros of that potential, right? Because, right, we know that in the limit I should be there. Otherwise, okay, you have some boundary layer appearing. So let's do the easy thing. And this is smooth. Okay, let's consider a smooth boundary data. And now I want to define, yeah, so okay, hope this is once you, so for the screen that, okay. So what is the topological degree of G? So what does it mean, topological degree? Okay, so this is our domain omega, and the boundary, so here you have something that moves into S1. Okay? So for such functions, you can define a topological degree, or what is called also a winding number. So what does it mean? It means that, so for example, let's say that you start from here and you look how G winds in S1, okay? And you look how many turns you did on S1 once you finish the loop, okay? So that is called the topological degree, and you have a formula for that. So consider that tau is the unit tangent vector field to omega. So this topological degree is the determinant between G and the tangent derivative of G. Okay, and you integrate all that. Okay, or if you think in terms of complex numbers, this is Ig tau G bar up to plus minus or something like this. So this is an integer. So in fact, if you want, so for example, you fix a point P. So of course, once you cut it here, this curve becomes simply connected, right? It's like an interval. So there you can write that in each point, G is like EI phi for some, right? For some phase phi, and in fact this will give you is nothing but right, how many times phi winds S1. So here you will have that this is 1/2 pi phi p plus minus phi p minus, right? But since G is continuous at least, so they can vary by a multiple of 2 pi, okay, and that's Z, okay. So I will focus only on minimizers of this, okay. So the problem that we want to study is this this problem of minimization. So we will minimize under this boundary constraint that U is G on the boundary, okay? So this is what we want to study. So always when at fixed epsilon. Maybe this epsilon will be small, but let's consider fixed. So always when you, this is a typical calculus of variation problem. So you have a functional, you minimize it. So there are three things that you study at the beginning: existence, uniqueness, regularity. Okay, and then of course the fourth step will be to study qualitative or quantitative properties of minimizers. So, so these are the three things we will study. So of course there is a functional framework, right? I mean, the first remark is in which space you study all this. So you remember from your functional analysis course, I hope that you introduced already H1 in distribution. We didn't reach to H1 yet, the space H1. Ah, you stopped. Okay. Did you heard about H1, the Sobolev space H1? Okay, doesn't matter. I want. Okay. Anyway, there is a. So what I want to say is that anyway, we will do it together in the distribution course. Okay. So these are L2 functions such that the gradient in the terms of distribution, this you know, is an L2 matrix, okay? So what I want to say is that this is in fact the space where the energy is finite. So when you look to the spaces where this energy is finite, you get exactly to this space. That is very nice, Hilbert space. Anyway, okay, fine. I won't speak anymore about H1. It's a pity that in your functional analysis you didn't do this. Okay. Okay. So first result is existence. Okay, existence of a minimizer. So this is very easy, I mean, very standard result in calculus of variation. This is the so-called the method, you use the method of the direct method in calculus of variation. So the answer is yes, always. And this is done by the direct method in calculus of variation. So let me explain. I mean, since we didn't get to the functional analysis framework, I just explain like this. So what is the direct method? You will consider a minimizing sequence. So this means you take a sequence of maps such that their energy will converge to the infimum. You don't know that this infimum exists, it's finite or not. Of course, it exists, it's because it's something positive. Right? So you take a minimizing sequence, and then what you look is to have some compactness. So in fact, in here you will have that this minimizing sequence is bounded as in your energy space, right, which is H1, and then you apply all your functional analysis notions that you have some weak convergence, and then you will just need to see that such an energy is lower semi-continuous with respect to the weak topology, and then you can pass to the limit, and you get the existence of a minimizer. Okay, so this is standard. Okay, that's the direct method in calculus of variation. Okay. So once you have a minimizer, then in such problems you will have a PD. Okay, so if U epsilon is a minimizer, let's call this problem min. Okay, So is a minimizer. Then what you have is that this is a critical point. So what does it mean is that once you take a test function, so now your test function should be also complex, right? So with values in R2 and 0 at the boundary. So think to our test function C infinity compactly supported, but you take two components. You will have that when you look to the energy U epsilon plus T psi, right? So once you fix psi, this is nothing but a 1D function that has the minimum in 0, right? In t equals 0. So this means that the derivative is 0. And then you just look, okay, you just differentiate that energy there. So what do you have? So you will keep only the linear part, right? The linear part inside that you have there. So what you have when you differentiate the Dirichlet, you get gradient U epsilon, gradient psi. And then when you differentiate like 1 minus t squared to the squared, right, the 4 goes away. So it's 1 over epsilon squared, 1 U epsilon square minus 1. And then it's U epsilon psi. Okay, that's the differential of this. And this is 0. Okay, and this should be true for every test function psi, and then you do the integration by parts, and then you get to this PD that is called the Ginzburg-Landau system, that is minus Laplacian U epsilon. Okay, that is, it's equal with 1 over epsilon squared, 1 minus U epsilon squared, U epsilon, so that's in omega, and then U epsilon is G at the boundary. Okay, so this is the 2D Ginzburg-Landau system, right? So there are two PDEs, scalar PDEs, right, that are coupled through the modulus, right? And this is something that we study. Okay, so uniqueness. This is, so if epsilon is large, so let's say epsilon is larger than a certain epsilon, you can check that that energy is strictly convex. Okay? So once you know that the energy is strictly convex, you know that the critical point is unique, right? And we always prove that, that the minimizer exists. So this means that the minimizer is the unique critical point. Okay, so here the answer is yes. The delicate thing is what's happening when epsilon is small. So the answer sometimes is no. So they are, depending on your boundary data, you can have loss of uniqueness, right? You can have multiple minimizers. Sometimes it's true. And this is maybe a question that I will address in the end, that uniqueness is something related in general with symmetry. Okay? So here it's yes and no. Okay? Okay, and now regularity. Well, you can prove that, in fact, any solution to the PDE is C infinity up to the boundary. Okay, and again, this is something that is quite standard in elliptic PDEs or systems, because what is the main step is to prove that, okay, you know, for systems, for scalar PDEs, scalar elliptic PDEs, a tool that is used is the maximum principle, right? When it's about systems, well, what does it mean positive? Okay, but what in here, what you still have a maximum of principle for the modulus. So the first step would be to prove that, right, this modulus of u epsilon is 1 at the boundary, right? Because G is with values in S1. So you can prove that, in fact, in the interior, this modulus decreases. So this already gives you that your every solution is in L infinity. And then you can use the machinery that is in the elliptic PDEs, the regularity of elliptic PDEs, that will tell you that this u epsilon is smooth. Okay? So then you will use the standard elliptic theory. Okay, so in some sense, if you remember the picture that is here, right? So these smooth functions will converge, if what I said is true, to these singular things. Okay, so that's why I was saying that such AK that is that's a singularity for that vector field, in fact, will represent a zero, okay, of this C infinity function. Okay. So let me do the two cases. So the first case is when the degree is 0, so which is the boring thing. So no vortices will be there. So degree of G is 0, and then the second case when the degree is different than 0, and this is where the nice things start to happen. Do you have questions up to now about the model and what we're trying to do? No? Yes?
What is the topological degree?
Okay. So the topological degree means that, so when you look, so is this quantity that is written there, but what does it mean? It means once G finish the loop, the turn on the boundary, you look how many turns it did on S1. Okay? And the winding number of topological degrees is exactly the number of times you wind it on S1. Okay, and how did I explain it? Is that you fix a point on the boundary, and then you write G as EI phi, right? It's a smooth function, such a phi exists. And you look, so you start with the phi of P, okay, that is like the limit on the left, right? And you move, and you finish with the limit of phi in P on from the right. Okay? P is a point. No matter what point you choose, it's there, P. Oh, the phase, right? G is with values in S1, so it means it has a phase. Right? Once you have, this is your G of x, right? It has an angle, right? And this angle, I call it phi of x. So G of x is EI phi of x. Is the angle. Yes?
Maybe you will tell that later, I don't know, but you are saying that degree G equal to 0 is an uninteresting case because we have...
Yeah, this is what I will, yeah, what I do, yes.
Whatever the peculiar boundary vortices can never...
Yeah, this is the theorem that, yeah. I speak about this and then about...
You said it's uninteresting, so I didn't know
Yes. No. The sequel of my talk is to do this and then this. Other questions? No? Okay, so let's start with bad publicity because now you will not look at this, but it's interesting. I mean, you learn it from this, a lot of things. So degree G is 0. What does it mean? So if you understood now what is the degree, it means that your phi, so the limits on the left and on the right are the same. Right? Is the same. So this means that you can write G as EI phi, and this phi is continuous, okay? But of course, then you look, once you have a continuous, then you look locally, and you can do a logarithm, right? Locally, and then you see that this is smooth also. So, in this case, coming back to the uniqueness, you can prove that when epsilon is small, the minimizer is always unique. Okay? So, if epsilon is small, in this case, then U epsilon is unique. So, U epsilon, the minimizer, because that is, now I'm saying the minimizer is unique. Okay, and this is a result of Ye and Zhu. In 96. Okay, so now so the theorem I want to, so I'm looking to the asymptotics, is the asymptotics of minimizer. So now the sequence I will look, it's unique, right? It's a unique sequence when epsilon is small. And the theorem that answers also to your question is the following. So this is the theorem of Betuel, Bresis, Hélin. '93, that tells you that as epsilon goes to 0, the minimizers behave as follows. So they will converge to U star in H1. You don't know, I don't write it. In any CK log of omega. So maybe something can happen at the boundary, but in the middle you go as smooth as you want. And also in C1 alpha up to the boundary for every alpha between 0 and 1. Okay, so this means that you can do in a topology where the derivatives stay Holder. Okay, so who's this U star? Well, it's the unique harmonic map with value seen as 1 that is G at the boundary. So where U star is the unique solution to the harmonic map problem. So now I will write you the equation. So careful. Harmonic map with value seen as 1 is not the Laplacian is 0. So in fact, the harmonic map, you should always think that it's a critical point of the Dirichlet energy when you restrict yourself to maps that could take values in some manifold. So here you start with values in S1. So if you remember from your optimization course, right, when you do minimization or under a constraint, then you will have a Lagrange multiplier. The thing is that this Lagrange multiplier is in any point. This constraint is in any point. It's not only in L2 or, yeah. So this means that the Lagrange multiplier is a function. And the Lagrange multiplier here is this gradient U squared. Okay? Okay, but in this case it's easy. So you can go to the usual harmonic problem, the scalar one. So more precisely, you can write this U star as, so it has a phase that will be a harmonic scalar function. So is the unique solution of, so this is a real harmonic, and phi star, so should be the phase. Okay, let me put phi 0 here. Okay, is the phase of yeah, of course the phase is up to a constant 2 pi, but 2 pi z, right? But you fix, because right, these are in S1, then you will not see anymore that thing. Okay, and what's the energy? So what's the energy of this with respect to this? Well, so moreover, we will have that the energy of U epsilon is nothing but, so these functions are in H1, okay? So because, right, there are no vortices, it's gradient of U star squared, and then it will be plus a small O of 1. Okay, so they converge. That's why there is a convergence in H1 that I didn't try because you don't know what's H1. Okay, and why this tell you that this is boring, that that no vortices appear? Well, because this U star, right? So here, this U star is smooth. Right, is smooth. Why? Because phi 0 is smooth, so then phi star is smooth, and then U star is smooth. So no singularity, right? No vortex. So this will tell you that U epsilon does not have zeros. Why? Well, because I told you that U epsilon converges to U star, in particular in L infinity, right? So this means that the modulus converges also to U star uniformly, which is 1. Okay, so after a certain epsilon, this modulus is larger than 1/2, so no 0. Okay. So that's why this is the boring case, but okay, I mean, Betuel-Brisier-Celan started with this, and then they wrote this green book that became the Bible in this topic. So let's go to, yes.
What is the normal procedure in these spaces where you're taking over this sort of function?
I'm sorry, here?
Yes.
It's just the right, in this space you have a norm, right? You just take, right? The norm that you consider you consider, right, the gradient in L infinity, and then you consider also the Hölder norm of this, right? And the Hölder alpha is like a okay. Okay. So let's go to the Bible, to the interesting thing where we need to understand vortices. So case 2. So degree of G is non-zero. So this means that once you finish your loop, then the limits there, they jump, right? So you can always write G like EI phi by this, but this phi has jumps. So if you want, you can see it as a BV functions, bounded variations, right? But okay, has jumps. Okay. So up to do a conjugation, you can consider always that this degree is positive, right? Otherwise, you will just look to G bar and the degree will change by the sign, right? So without loss of generality, we can assume that the degree is strictly positive. Otherwise, you do the conjugation, complex conjugation. So as I said, when epsilon goes to 0, we expect vortices, and in fact what will happen is that you will expect vortices of degree 1. So the prototype is the vortex of degree 1, which is this x over modulus of x up to a translation, up to a rotation. Okay, so it's like 0 here, and right, it's like this. Okay, so this is right. It's a singular S1 harmonic map. Right, I mean, this function you can check. It also verifies that equation that PDs, for example, in the classical way away from 0, because right, this is smooth away from 0. Okay, and what will happen when epsilon is larger than 0? So how the system, right? Because so how will be U epsilon? So we know U epsilon should be smooth. So in some sense, you want to regularize such a singularity, okay, by keeping degree 1, topological degree 1, right? So here the D, right, is so when you compute the degree of U star on some circle, let's say on the boundary of B1, of course this is 1, right? Because this is EI theta. The D there is 1. So how you will do it so you will have something that keeps this structure, but in the middle, so outside a ball of radius epsilon, so the epsilon that is in the energy plays the role of the length scale of your vortex. So here, U epsilon is expected to behave exactly like this, like x over modulus of x, but you should have some profile that will bring you to 0 in the middle. Okay, so this profile, what is this profile? So the profile is something like this. So this f epsilon is stays always below 1. So in 0 it's 0, and then it grows fastly, and then it stays below 1. Okay, so let's say that in 1 reaches 1. Okay, and this is the shape of this f epsilon, and it depends only on the radius. Okay, so this is the expectation, the structure, the expected structure of the vortex of degree 1 when epsilon is strictly positive. Okay, so now the energy, right, since you expect that this converges to this, should blow up, and we can really see that it will blow up like a log epsilon. So again, let's assume that this is the ball of radius 1. So when we compute such a thing, so the potential part stays of order 1. So this is the thing that it blows up. So here also you will stay of order 1. So this is like looking of what's happening between B1 and B epsilon. And there, what I said is that this is like 1. So this is like gradient of x over modulus of x. And this is, we already computed this, right? It's like 2 pi integral from epsilon to 1 of dr over r, so it's log epsilon. Okay, so you expect that the minimizers will blow up in energy like log epsilon. Okay, so this is where the renormalizing procedure starts to play in physics. Always when you have something that, a quantity that blows up, what you do is that you will try to isolate it, and then to look what's happened at the next order. And at the next order, you will start to see how these vortices interact once each other. And this is something that will tell you what is their optimal position. So the theorem, so this is the theorem that gives you everything, or at least the first feature. So this is Bézies, Bétuel, Bézies, Célin. Okay, so this is their book. It's a wonderful book. So if the degree of G is strictly positive, then, so what's happening now is that when epsilon is small, the minimizers are not unique in general, right? So what you do is that, okay, you take a sequence of minimizing sequence, and then maybe up to a subsequence they will converge. So then up to a subsequence, U epsilon, so these are the minimizers, some minimizers of our problem when epsilon is, will converge to U star, and this U star writes like this. So let me do the picture in the same time. Okay, so these are the vortices of degree 1. Okay, and then there is a correction of some, how did I know, 5 star. Okay, so, so it converges in which sense? In CK log, but now away from these vortices. And C1 alpha lock up to the boundary, but away from these vortices. Okay, where? So I have to explain what are these things. So where phi star is harmonic, so this part is smooth. The singularities are here. And of course, this U star is G at the boundary. Okay? And this is what is important. And A1 to AD are distinct vortex points, vortices of degree 1. So in some sense, what's happening here is that if in the middle, if in the limit you would think that you have a vortex of degree 2, if you remember the first computation that we did, that is like d squared. Okay, so a degree 2 will catch you an energy of like 4 times log. But what you can do is that you can split the vortex of degree 2 into vortices of degree 1. So each degree of vortex of degree 1 will come with like 1 energy. So 1 plus 1 is 2, which is less than 4. So when you look to the minimal level, already will tell you, no, degree 2 is too much, too expensive. And in fact, okay, you can even prove that the degree 2 will become unstable when epsilon is small. Okay, so it's not a minimizer. Okay, so this is fundamental. Okay, so they will converge to this. And now, energetically point of view, okay, I'm talk too much. So moreover, what is the energy? So the energy, so of course it will come with this quantized energy for each vortex, which is like log epsilon. That's right, in our energy is like 1/2. Right, so then it's pi. So then you have d vortices, so it's d pi log epsilon. And then it's something of order 1. And here it's where the renormalized energy starts to play. Okay? So let's understand that O of 1 energy, so the renormalized energy. May I have 3 more minutes? Thanks. Because that's the essential part. So this O of 1 is the so-called interaction between the vortices. So that's the interaction. And then you have a quantized constant that comes from the radial profile of a vortex. So it's d times a gamma, a constant, plus a small O of 1. Okay, once you reach to small O of 1 is good. Okay, and now let me explain you this quantity, which is fundamental, which is like the logarithmic repulsion that you can see in many other physical domains, models. It's kind of Coulomb, yeah, which gives logarithmic and energetic cost repulsion. So so how do you compute this interaction between the vortices? So what do you do? Let me draw again the picture. Okay, we know that if we look to the limit energy, this is blowing up here. So what you do, so again, this is the renormalizing procedure here, you cut it off. You cut it off at the radius r, okay? So you look what's happening outside. Okay, and then you have to withdraw the infinite part that you took out, and the infinite part will be like a logarithm of this r. Okay, and then this is the x, and then you take the limit when r goes to 0. Okay, this limit exists, etc. Okay, what we do is kosher. Okay. So this is the renormalized energy. Okay, you'll say, okay, well, it's a nice formula, give me a number. Okay, so this behaves like minus pi sum of the logs of aj minus ak plus tanana. So this is at the first order, this is what you have. So here you can see already that you have repulsion. Why? Because when aj goes to ak, this is close to 0, right? So, but this is a minus log. So this goes to plus infinity. So it's too much. Because, in fact, what's happening is that this configuration, since I took minimizers, will also minimize this renormalized energy. Okay? So this is the repulsion of vortices. Okay?
Just to check.
Yes.
I guess that despite the fact that you write the value of A1 and etc. to AB, there is also the function phi star, which intervenes in the definition of the value.
Right. So phi star is already there. Right. But of course, it does not come here. It will come at the order O of 1. Yes. Yes. Correct. Okay, and the constant gamma, so it's nothing but you take the minimizer in the unit disk with respect to the data gx equal x. Okay. You withdraw the infinite part and then you make epsilon goes to 0. So this is what is called that in some sense you look only to the profile f epsilon that I draw it there. So this is nothing but the energy of the optimal f epsilon that will satisfy some ODE. Okay, and I stop here. So since u epsilon are minimizers, this means that A1, AD are minimizers of this functional. Okay? So you see, this you can write only in terms of AJ. Of course, it's something that is the boundary G that will play the role. Okay? But so it has some formula. So in some sense, in order to see where these points will be situated, well, this is a functional that is with D complex variables. So there are numerical simulations that tells you where they are. So this is when D goes to infinity. This is the famous Abrikosov lattice. Okay, Abrikosov that got the Nobel Prize doing superconductivity and playing with this. Okay, then I stop here. Thank you.
Thank you very much. Other questions or remarks?
Just a question concerning the last but one word that you said. It's the what lattice?
The Abrikosov lattice.
Abrikosov.
Abrikosov, right? It's the Nobel Prize in physics. Yeah. Yes.
In the first paragraph, we say that two star we write in 3 star, and 3 star the solution of Dirichlet problem.
Yeah, that's the right. You start in the case degree 0. Yes.
Okay, yeah, but in the Dirichlet problem, in general, it maybe not have the solution. We need some condition on omega to ensure that it has a unique solution.
So are you speaking about this? Yes. Okay. So when you look to maps that are in H1 with values in S1, you always know that there exists a unique phase up to 2 pi that stays in H1. Okay. So what I want to say is that this is equivalent exactly with this, and this you know that has a unique solution, right? So what I want to say is, so in order to see how you pass from here to here, is that if you have U, okay, I have to speak about H1. Or finite energy, or yeah, okay. So you remember what I said, that it's an L2 function, then the gradient stays in L2, okay? So once you have a function like this, there is a theorem that will tell you that there exists a unique phase up to 2 pi in H1 omega r, such that U is EI phi, and when you do the computation, you get that gradient U is gradient phi, okay? So, right, I was saying that these are nothing but critical points of the Dirichlet functional, right? So this is the same, right? And of course, right, this you have uniqueness because it's a convex function for scalar, yeah? So, yeah, no problem. Yeah, there you have it. Very good question. So yes, so they are. The problem is what? So that depends. What do you mean by higher dimension? So if I speak about B3 with values in R3, or if I speak about B3 with values and I stay in R2. So if I speak, let's put it like this. If I speak about B3 with values in R2, so I still stay complex, then of course, right, I don't have a disk now, I have a ball. This is what is called, you will have vortex filaments. So in some sense, when you restrict yourself to a section, it's like the problem we discussed, so you have a point. But then in every other section, you will have other points. So that's a filament. Okay. So then you can you can replay the thing. The problem is that this renormalized energy, you don't have a formula in general, because imagine that your filaments are not vertical. If they are almost vertical, you can do it. This is, you just do decomposition by sections, you can do it. But if, can they collapse or something like this? These are really things that are still open. Okay, now in the other case, when you look from B3 to R3, okay, so in some sense at the limit you will have B3 to S2, okay? So you can still have this kind of vortices x over modulus of x. which in dimension 3, right, when you look to that computation up there, right, you will have that now it's something that is finite energy, right, because you have 1 over r squared, but the volume is r2dr. So they have finite energy. So this means that if you, of course, they will come with a quantized energy, these vortices, but in order to see what's happening at the next order, you have to see still of something of order 1. So now they are you have some things that are starting to be done. In fact, our colleague Xavier Lamy has something on this. But yeah, so these are really delicate things. So I mean, since 35 years, as Mihai said, a lot of things were done, but a lot of open problems still there. Yes?
Is there another model different from that one that you saw at the beginning where the stereo vortices come up?
Yes, yeah, right. So liquid crystals. There is, so there are several theories in liquid crystals. Liquid crystals is, for example, you look on your cell phone, right? This is LCD, right? Liquid crystal display, right? So, of course, you don't want to have vortices, right? Singularities on your screen. So it's something that is important. So, okay, but there are several theories. So for vector fields, Q tensors. So in some sense, the variables, the system is more complex than that. So, so for example, in what is nowadays very fancy, this Landau-Deugen theory, you speak on maps that takes values from the disk or the ball in R3, but with values in something that is dimension 5. Okay? So of course, for example, here you can always define what's a topological degree from a sphere to the same sphere, same dimension. But you don't know what does it mean. There is no dimension, no notion of topological, right? And so this means that the structure of singularities are much richer than that. But there are regimes where you can do this. So also there, this is the basis. You start from this, so that's why I call this like the baby model that you start to apply in. So in general, it's always, the systems you will look will be very complicated. The thing is that you start to reduce variables, but keeping the feature that you want to, right? And once you understand your baby model, then you will add another variable and see, can I do the things? If yes, then I can add the second one. But you should really understand what's the main objects, and this is the baby model. Yeah.
Questions? If not, let's thank Radu again.
Yeah, thanks, Mihai.